We often treat databases as magical vaults, distinct from the loose stack of papers that represents a text file. We assume that because a database feels faster and more secure, it must be built from a different kind of material. This distinction exists only in the software. At the level of the hardware, a database uses the same physical reality as any other file. To find the source of a database's power, we have to look past the user interface and the operating system, descending until we touch the physical computing hardware. Down here, at the silicon level, both files and databases reduce to the same components: electrical charges on an SSD, memory blocks and RAM, and CPU instructions processing bytes. Since the hardware is identical, a database's capability is a product of architecture. Its power comes from an invented software engine that imposes a strict mechanical discipline on those bytes. The foundational unit of this discipline is the page. Databases avoid managing data character by character. Instead, they organize raw information into uniform, predictable chunks. When data is needed, the system copies these specific pages from the stable disk into the temporary workspace of RAM. Logic happens only in memory. The CPU cannot evaluate conditions or compare values while they sit on a hard drive. It requires the data to be loaded into these memory pages first. A standard text file forces the application to ingest a continuous stream of bytes, scanning forward without an internal map. By organizing storage into managed pages, the database acts as its own internal operating system. It tracks which pages are on disk and which are in RAM, creating the physical foundation for high-speed execution. The difference in these approaches becomes clear when we try to find one specific piece of data, such as a single user ID. Reading a basic text file requires a brute force scan. The CPU starts at the beginning and evaluates every byte sequentially until it reaches a match. On a large dataset, this forces the hardware to load massive amounts of irrelevant data into memory, consuming time and processing power that scales poorly as the data grows. A database intercepts this request. During the parsing phase, it converts the raw text of a query into a structured internal representation of the task. In the planning phase, the engine consults its metadata to calculate the path of least resistance to the data. To bypass the need for a full scan, the planner relies on the index. The index is a separate memory structure that serves as a searchable topological map of the records. The CPU traverses this index with a few mathematical comparisons. It isolates the storage location of the target row before moving any actual data pages. Because the location is known, the database loads only the single required page into RAM. It ignores the vast majority of the disk volume. Every database query represents a coordinated CPU navigation through structural paths. Speed is the byproduct of systematically avoiding physical hardware I/O. While reading is about fetching existing records, writing is about managing state during a change. Consider the mechanics of transferring funds between account A and account B. If the hardware loses power after the system deducts from account A, but before it adds to account B, the data is corrupted. A plain text file attempts to overwrite bytes on the disk directly. It has no internal mechanism to defend against a partial hardware failure. A database uses a transaction to create a logical boundary. It guarantees all related changes execute as a single unit or none are applied. This guarantee relies on a specific architectural component, the write-ahead log. Before changing the final data, the database records its intent in this sequential append-only log. Only after the intent is locked to stable storage does the system modify the data page in RAM to reflect the new balance. This creates the commit boundary, marking the transaction as the authoritative state. This ensures that even after a failure, the change is recognized as committed. If the system crashes, the recovery engine inspects the log. It replays committed intents and rolls back any partial, uncommitted changes to ensure consistency. Because database writes function as governed transitions, they maintain integrity where a simple file edit would leave the state in an unfinished, broken condition. These internal mechanisms, pages, indexes, and logs, explain why different database architectures exist. All databases run on the same silicon, but they reorganize these components to meet different pressures. Relational databases prioritize strict schemas and interconnected relations for transaction safety. Key value stores remove heavy logging and planning to achieve extreme in-memory speed for lookups. Document databases abandon rigid tables to store data in flexible, hierarchical objects. Selecting a database type defines the mechanical trade-off, speed, safety, or flexibility required to solve a specific problem on that hardware. This diversity exists because database engines are engineered software architectures, each shaped by a different class of computational workload. Having seen the machinery at work, we can ascend back up the stack, leaving the physical grid of silicon and pages. We move past the transaction logs and state management layers protecting the data. We pass through the navigational layers, the indexes mapping the hardware below. We return to the high-level interface, arriving at the same pulsing cursor where the query began. This interface is a necessary abstraction. It allows us to interact with data without managing the immense complexity of the hardware ourselves. Seeing the machinery beneath the cursor replaces the magic box mental model with a clear view of the engineering required to move, protect, and search bytes at scale.